Somewhere right now, more than 13 billion miles from where you are sitting, a machine built in 1977 is humming. Not literally, because there is no air out there for sound to travel through. No atmosphere, no medium of any kind. But if you take the raw electrical signal this machine is recording and run it through a speaker here on Earth, you hear something. A low, eerie, constant tone, rising and falling in pitch, coming from a region of the universe no instrument built by human beings has ever sampled before. NASA scientists have confirmed exactly what the tone is, where it is coming from, and why it should not be there the way it is. And once you understand what this frequency actually represents, it becomes one of the strangest and most genuinely important recordings our species has ever captured. This is the real story of the frequency Voyager 2 is picking up from beyond the edge of our solar system, why it took scientists years to confirm it was not a mistake, and why the window we have left to keep listening to it is closing faster than most people realize. Stick with me, because this story connects a launch from 1977, a legendary scientist who spent 5 decades of his life listening to exactly this kind of signal, a boundary in space that behaves nothing like the textbooks predicted, and a power crisis unfolding on this exact spacecraft right now in the summer of 2026. That could determine whether we keep hearing this frequency at all. If stories like this are the kind of thing you want more of, subscribe now, because we are only getting started, and there's a lot more to this than any headline has actually explained. Let's start with where Voyager 2 actually came from, because almost nobody remembers the full story anymore. It launched on August 20th, 1977 from Cape Canaveral, 16 days before its more famous twin, Voyager 1, followed it into space. The mission on paper was modest, almost embarrassingly so, given what eventually happened. Fly past Jupiter, fly past Saturn, take pictures, gather data, then quietly retire sometime around 1981 once the fuel and the funding ran out. Nobody involved in building this spacecraft wrote anything into the mission plan about reaching the edge of the solar system, because nobody at the time knew for certain that edge could even be reached, or what it would actually look like if a machine ever got there. What happened instead is one of the most extraordinary extended careers any machine built by human hands has ever had. Engineers at NASA's Jet Propulsion Laboratory had noticed something rare in the late 1960s, a natural alignment of the 4 giant outer planets, Jupiter, Saturn, Uranus, and Neptune, that happens only once every 176 years, allowing a single spacecraft to use the gravity of each planet in sequence to slingshot toward the next one, saving decades of travel time no rocket of that era could otherwise provide. That alignment was happening in the late 1970s. Voyager 2 was built specifically to take advantage of it, given a longer, more ambitious trajectory than its twin, one that would let it keep going after Saturn instead of leaving the plane of the planets entirely. It reached Jupiter in July 1979, discovering a previously unknown 14th moon along the way. It reached Saturn in August 1981, mapping ring structures in detail no Earth-based telescope could ever achieve. Then, instead of ending the mission there, engineers extended it toward Uranus, and in January 1986, Voyager 2 became the only spacecraft in human history to fly past that planet, discovering 11 new moons, 2 new rings, and a magnetic field tilted a bizarre 59 degrees away from the planet's axis of rotation. A discovery so strange, it still challenges the models scientists use to explain how planetary magnetic fields form in the first place. 3 years later, in August 1989, it reached Neptune, the final planetary encounter of the entire mission, discovering the Great Dark Spot, an Earth-sized storm tearing through Neptune's atmosphere, measuring wind speeds above only 300 miles per hour, the fastest ever recorded anywhere in the solar system, and finding active nitrogen geysers erupting from the surface of Neptune's largest moon, Triton, a world now believed to be a captured object originally born far out in the Kuiper Belt. After Neptune, the cameras were switched off permanently. There was nothing left to photograph. Mission planners could have ended the story there, and it already would have been one of the greatest achievements in the history of space exploration. Instead, they turned the spacecraft outward, toward the true edge of everything the sun's influence touches, and kept listening. This is the part of the story that most people simply never hear, because the headlines almost always go to Voyager 1, which reached the boundary of the solar system first, crossing into interstellar space in August 2012. That boundary is called the heliopause, and it marks the outer edge of the heliosphere, the enormous bubble carved out by the sun's constant stream of charged particles, known as the solar wind, a bubble that contains every planet, every moon, every asteroid, and every living thing we know of. Cross the heliopause, and you're no longer in the sun's neighborhood in any meaningful sense. You are in the space between stars. But here's the detail almost nobody outside the mission itself ever mentions, and it matters enormously for understanding the frequency at the center of this story. Voyager 1's plasma science instrument, the device specifically built to directly measure the density and behavior of charged particles around the spacecraft, had already failed. It stopped working in 1980, more than 3 decades before Voyager 1 ever reached the heliopause. Voyager 2's equivalent instrument kept running. And that single fact is the reason this entire story about a mysterious frequency exists at all. Every spacecraft in deep space carries an instrument called a plasma wave subsystem, a device designed to detect oscillations in the ionized gas, or plasma, that fills the space around it. Here is the part that genuinely surprises most people the first time they hear it explained properly. There is no sound in space. It is a vacuum, and a vacuum has no air, no medium capable of carrying a sound wave the way it travels through the atmosphere here on Earth. What the plasma wave instrument actually measures is something completely different, the oscillation of electrons moving back and forth within the surrounding plasma, creating what physicists call an electrostatic wave. It has nothing to do with pressure waves in the atmosphere the way ordinary sound does. But by a genuine coincidence of physics, the frequency of these electron oscillations happens to fall within the same range the human ear can process, somewhere between a few hundred and a few thousand hertz, which means if you take that raw electrical data and run it through an ordinary loudspeaker, you can genuinely listen to it. Not as a metaphor, literally hear it. Don Gurnett, the physicist who led the plasma wave investigation on both Voyager spacecraft for the University of Iowa for decades, first played this recording publicly at a NASA press conference in September 2013, describing it at the time as a historic event, the first time humanity had ever produced an actual recording of activity occurring in interstellar space. When Voyager 1 was still inside the heliosphere, those oscillations sat at a low tone, around 300 hertz, consistent with the thin, hot plasma of the solar wind. The moment it crossed into interstellar space, the pitch jumped sharply higher into a range between 2 and 3 kilohertz, the unmistakable signature of colder, denser interstellar plasma pressing in around the spacecraft. That single measurable change in pitch was, on its own, hard scientific evidence of the crossing, independent of any other instrument on board. Now here's where Voyager 2 enters the story in a way that changes everything, because unlike its twin, Voyager 2's plasma instruments were still fully alive when it finally reached the same boundary 6 years later, on November 5, 2018, at a distance of roughly 119. 7 astronomical units from the Sun, just under 11 billion miles out. And what those instruments picked up did not simply confirm what Voyager 1 had found. It complicated it, deepened it, and in some places directly contradicted the assumptions scientists had been working with for 6 full years based on incomplete data. 5 separate peer-reviewed papers describing Voyager 2's crossing were published together in the journal Nature Astronomy in November 2019, and the picture they painted was stranger than anyone expected. Scientists had assumed the heliopause would behave like a relatively narrow, sharply defined line, a thin transition zone where the hot solar wind gave way cleanly to the colder interstellar medium. Voyager 2 found something closer to a coastline, a genuine transitional layer roughly 100 million miles wide, filled with interstellar particles that had already pushed inward through the boundary before the spacecraft technically crossed it, mixing with solar material in ways the earlier models never predicted. The instruments also produced the first ever direct, simultaneous measurement of plasma temperature and density on both sides of the boundary at once. The interstellar plasma outside the heliopause came in at a directly measured temperature between 30,000 and 50,000 degrees Kelvin, far cooler than the tens of millions of degrees measured just inside the boundary, but roughly half of what earlier theoretical estimates had predicted for interstellar space. And the density of that plasma turned out to be more than 40 times greater than the density of the solar wind at the same boundary, confirming that the space between stars, far from being an empty void, is actually a thicker, more substantial environment than the thin protective bubble our entire solar system sits inside. Stamatios Kremigis, a senior scientist on the mission at the Johns Hopkins Applied Physics Laboratory, pointed to something in the data that genuinely stunned the team. Voyager 1 had crossed the heliopause during a period of high solar activity. Voyager 2 crossed during the opposite extreme, a period of low solar activity, when existing models predicted the boundary should sit at a noticeably different distance from the Sun. Instead, both spacecraft found the edge at almost exactly the same distance. Voyager 1 at 121, 6 astronomical units, and Voyager 2 at 119 astronomical units. Kremigis said it plainly at the time, "We don't understand why that is." Coming from a scientist who had spent decades working with this exact data, that admission was a genuine signal that something fundamental about how the Sun's activity relates to the size of its own protective bubble simply does not work the way the textbooks describe. But the finding that Ed Stone, the mission's longtime chief scientist, called the most remarkable result of the entire crossing was something even stranger. The heliopause leaks. Not metaphorically, literally. Particles cross that boundary in both directions, constantly, a behavior nobody had fully appreciated before these 2 spacecraft provided direct measurements from 2 different points on the boundary at 2 different times, approaching from 2 different directions. Voyager 1 detected interstellar material pushing inward before it fully crossed. Voyager 2, approaching from a different angle entirely, detected a trickle of low-energy solar particles leaking outward into interstellar space before it had even reached the heliopause. Stone summarized the underlying discovery in words worth sitting with. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars in the Milky Way, he said. Not where the sun ends. How the sun interacts with what lies beyond it. That is a fundamentally different picture of our place in the galaxy than the one most people grew up with, and the frequency Voyager 2 is still recording right now is the ongoing, real-time evidence of exactly that interaction. Because here is what makes this story matter today, rather than simply as history from 2018. The frequency did not stop. It kept going. Researchers analyzing years of continuous data from the plasma wave instruments eventually discovered something nobody had specifically been looking for. A persistent narrowband electron oscillation that shows up continuously in the data starting around 2017, not as a single event triggered by a passing solar shock wave the way earlier plasma oscillation detections had been, but as an ongoing, steady hum stretching across hundreds of millions of miles of interstellar space year after year. A team led by Stella Koch-Ocker at Cornell University, publishing in Nature Astronomy, described this persistent emission as something genuinely new. A continuous signal that lets scientists track the density of interstellar plasma, the way a weather station tracks conditions over time, rather than only catching isolated snapshots triggered by rare solar events. Before this discovery, measurements of interstellar plasma density were sparse and scattered, essentially isolated data points collected only when a shock wave from a distant solar eruption happened to ripple far enough outward to disturb the plasma near the spacecraft. What the persistent frequency provides instead is closer to a running, continuous portrait, revealing that interstellar space has genuine structure and texture at scales ranging from mere meters up to distances measured in millions of miles, a level of fine-grained turbulence that was completely invisible to any instrument before a spacecraft was physically sitting inside that environment to measure it directly. Scientists studying this persistent frequency have identified two competing explanations for exactly what is generating it, and as of the most recent published analysis, they still have not been able to determine with certainty which one is correct. The first possibility is that the signal comes from thermally excited plasma oscillations, essentially the natural, ordinary vibration of charged particles interacting with their surroundings. This would still be a genuinely significant discovery, but it would fit inside existing physical frameworks without requiring scientists to rebuild their models from the ground up. The second possibility is something called quasi-thermal noise, a different underlying physical mechanism that carries information about the density and temperature of the surrounding plasma in a subtly different way. One that would require the existing models of the interstellar medium to be meaningfully revised. Distinguishing between these two explanations requires either years of additional data from instruments that are producing less and less of it as power runs out, or an entirely new mission built specifically to study interstellar space with instruments engineered for exactly this purpose. No such mission currently exists, and none is currently funded. If one were approved and built starting today, it would take at least 25 years just to reach the same boundary Voyager 2 already crossed back in 2018. Voyager 2's own version of this frequency, separate from, but closely related to what its twin recorded, has continued to draw attention from researchers, precisely because it is steadier and more consistently detailed than the equivalent signal from Voyager 1, giving scientists something close to a stereo picture of how interstellar plasma behaves when sampled from two different points in the sky at once. The eerie, constant hum recorded by Voyager 2's plasma wave subsystem confirms something that sounds almost poetic once you actually understand the physics behind it. Interstellar space is not silent. It is not empty. It is, in a very real physical sense, alive with motion, structure, and constant low-level activity that no telescope pointed outward from Earth could ever have detected on its own. Every one of these findings matters far beyond simple curiosity, because the same boundary generating this frequency, the heliopause, functions as a genuine shield, deflecting the most dangerous forms of galactic cosmic radiation away from the inner solar system. If that shield behaves in ways more turbulent, more permeable, and more dynamic than existing models suggest, the long-term implications for understanding how life on Earth has been protected across geological timescales become a serious open question rather than a settled one. If a story like this is the kind of thing that genuinely interests you, take a moment right now to hit the like button, because it helps this kind of carefully sourced, fact-checked explanation reach more people who would actually appreciate hearing the real science instead of an exaggerated headline. Now, let's talk about what is actually happening to the spacecraft generating this frequency right now in the summer of 2026, because the timeline here is far tighter than most people realize. Every system aboard both Voyager spacecraft runs on electricity, generated by 3 radioisotope thermoelectric generators, sealed containers of plutonium-238 that produce heat as the plutonium steadily decays, heat converted directly into usable power. At launch in 1977, those generators produced approximately 470 watts, because plutonium-238 has a half-life of roughly 74 years, that output declines permanently and predictably, losing around 4 watts of available electricity every single year, with no way to refuel or reverse the process. Today, after nearly 49 years of continuous operation, both spacecraft are running on roughly 2/3 of their original power budget, and mission engineers have spent more than a decade managing an increasingly brutal set of trade-offs, switching off one instrument at a time to keep the transmitter and the heaters that prevent the electronics from freezing permanently alive for as long as possible. Since 2024 alone, the dwindling power supply has already forced the mission to permanently shut down 2 more science instruments on each spacecraft. Voyager 2's plasma science instrument, the original device responsible for its historic 2018 heliopause measurements, was itself switched off in 2024, its primary scientific purpose largely fulfilled once the spacecraft had moved well beyond the specific boundary it was built to study. The plasma wave subsystem generating the persistent frequency this entire story is built around, however, remains active, one of only 3 instruments still running on Voyager 2 today, alongside its magnetometer and its cosmic ray subsystem. Without some kind of intervention, mission engineers calculated that Voyager 2 would have been forced to shut down yet another one of those 3 remaining instruments before the end of 2026. Losing an instrument like that is never a small decision. Every instrument switched off represents a category of scientific questions that will simply never be answered, because there is no way to send a replacement spacecraft that far within any relevant time frame, and no way to ever switch an instrument back on once its shutdown is finalized. So instead of accepting that loss, a team of engineers at NASA's Jet Propulsion Laboratory spent roughly a full year developing an alternative, a technique so aggressive and so unlike anything attempted before on either spacecraft that they gave it a name borrowed from the origin of the universe itself. They called it the Big Bang. The idea was to completely restructure how electrical power flows through Voyager 2's remaining systems all at once, powering down a group of devices and simultaneously swapping them for lower power alternatives capable of doing the same essential job for less electricity, all while making certain the electronics stayed warm enough to avoid freezing permanently in the extreme cold of interstellar space. Every command involved in this procedure had to travel across a communication link stretching more than 19 hours one way, meaning a single exchange. A command sent up and a confirmation sent back down cost the team the better part of 2 full days, with no opportunity to intervene in real time if anything unexpected happened mid-procedure. In the first days of August 2026, NASA confirmed that the Big Bang procedure had succeeded. According to the mission team, the results matched their predictions so closely that engineers completed the entire reconfiguration exactly as planned, without needing to alter their approach mid-procedure. Kareem Badaruddin, one of the engineers who led the effort, described it afterward as a team effort representing the culmination of a full year of work, with almost every single member of the mission team contributing. The result is that Voyager 2's 3 remaining instruments, including the plasma wave subsystem responsible for the frequency this story revolves around, now have enough power to keep running for at least another full year longer than they otherwise would have. That success matters enormously beyond Voyager 2 itself, because the procedure was always designed as a proof of concept, a live test performed on the spacecraft slightly closer to home and slightly better supplied with power, so that if anything went wrong, the consequences would be marginally less severe than attempting the same untested procedure on its more distant twin first. Voyager 1 currently needs this kind of intervention even more urgently. In February 2026, during a routine maneuver that rolled the spacecraft to point an instrument at a different target, Voyager 1's onboard systems detected a sudden, unexpected drop in available power, forcing engineers into an emergency response despite a communication delay working against them at every step. Acting as quickly as a system with a round-trip time well beyond a full day possibly allows, the team made the difficult call to permanently switch off Voyager 1's low-energy charged particle instrument on April 17, 2026, leaving that spacecraft running on just 2 active science instruments, its lowest count of the entire mission. With the Big Bang now confirmed successful on Voyager 2, engineers are planning to attempt the same reconfiguration on Voyager 1 in the coming months, hoping not only to stabilize its remaining instruments, but potentially to bring the low-energy charged particle instrument back online. Nothing about that outcome is guaranteed, since Voyager 1 sits farther from Earth with an even longer communication delay and a thinner power margin. But the successful test on Voyager 2 gives the team something they did not have before this month: genuine confidence that the underlying engineering works exactly as calculated across a gap of nearly a full day in each direction. There's also a second milestone converging on this same window of time, one that has nothing to do with power budgets and everything to do with pure, staggering distance. On November 18th, 2026, at 2:16 and 7 seconds in the morning Pacific Standard Time, Voyager 1 will reach a distance of precisely 16,094,999,096 miles from Earth, a distance so vast it equals exactly one light day, the distance a beam of light covers in 24 full hours. No human-made object has ever reached that distance before, and none is expected to reach it again for a very long time after Voyager 1 eventually falls silent. Voyager 2, still trailing at roughly 13 billion miles out thanks to the longer four-planet route it took decades ago, is not far behind on the same outward trajectory, both spacecraft escaping the solar system in different directions at more than 3 astronomical units per year. Think about what that means for the team still operating these machines and still listening to the frequency they generate. Send a command to Voyager 1 on a Monday, and you will not know whether it arrived until Tuesday. You will not receive the response until Wednesday. Every diagnostic exchange, every careful step of a procedure like the Big Bang, costs a minimum of 2 full days just to complete one round of communication. And that gap will only keep growing as both spacecraft push outward at more than 35,000 miles an hour. Before we go further, I want to pause on something that connects everything in this story together, because it is easy to talk about instruments and frequencies and forget that behind every one of those measurements was a specific human being who spent his entire career listening for exactly this kind of signal. Ed Stone was 36 years old in 1972 when NASA handed him the position of chief scientist for the Voyager mission, years before either spacecraft had even been built. He held that position for the next 50 years, guiding the mission through its planetary flybys, through the long silent decades of the Interstellar cruise, through both heliopause crossings, and through the discovery of the very frequency this story is built around. He retired from the role in 2022 and died on June 9, 2024, at the age of 88, having spent more than half a century of his life connected to 2 machines that were still, at the moment of his death, actively transmitting data back from beyond the edge of the world he had spent his career studying. Colleagues described him as a trailblazer who dared mighty things in space, whose steady leadership held together one of the most ambitious and longest-running scientific missions humanity has ever attempted. The mission's own social media account, written for years in the voice of the spacecraft itself, marked his passing with a line worth repeating. Here, thank you for opening the door to our celestial exploration. Your legacy lives on beyond the heliosphere. And it genuinely does. The frequency Voyager 2 is picking up right now is still being interpreted by the team he trained and left behind, still carrying forward a relationship with these machines that has now outlived the man who understood them longer than anyone alive. If you have made it this far into the story, drop a comment and tell me honestly whether you had ever heard about this frequency before today, because so much of the public conversation around these 2 spacecraft focuses on distance and power levels, and the actual sound they are recording from interstellar space rarely gets the attention it deserves. And if you know someone who would genuinely enjoy hearing this explained properly, go ahead and share this with them, because stories like this one tend to get buried under vague, sensational headlines, and the real version deserves to travel just as far as the signal itself. Consider everything that single plasma instrument on Voyager 2 has given scientists that they otherwise would never have had access to. Before its 2018 crossing, essentially everything researchers thought they understood about conditions in interstellar space came from indirect inference and theoretical modeling, built on observations made from the relative safety of our own solar system. Voyager 2 turned that theoretical picture into a direct, measured, continuously updated reality, and in doing so revealed a boundary considerably messier, more permeable, and more dynamic than the clean textbook diagrams ever suggested. That reality is quite literally audible right now, in the form of a persistent electron hum rising and falling somewhere beyond the edge of everything the sun touches, still being recorded, still being translated into a frequency human ears can process, and still being studied by scientists who, years after first detecting it, still cannot say with total certainty exactly what is generating it. That is really what is at stake every single time engineers at JPL make one of these increasingly difficult calls about which system to save and which to sacrifice. It is not simply about extending the operational life of an old piece of hardware for sentimental reasons, although the sentiment is real and it is earned. It is about keeping open, for as long as physically possible, the only real-time window humanity currently has into a region of the universe that no other instrument has ever directly sampled, and the only source we currently have for a frequency that may be telling us something fundamental about the true structure of the space between stars. When Voyager 2's last functioning instrument finally falls silent, whenever that day arrives, sometime in the early 2030s, if current power projections hold, that window will not simply pause. It will close completely, and it will likely stay closed for decades because nothing capable of replacing it currently exists or is funded to exist anytime soon. There will be no dramatic final transmission, no last message decoded triumphantly in a control room somewhere. The signal will simply, gradually, weaken past the point where even the most sensitive receiving dishes on Earth, the enormous radio antennas of NASA's deep space network spread across California, Spain, and Australia, so that one is always facing the right direction as the Earth rotates, can still pull it out of the background noise of the universe. And then, after nearly half a century of continuous contact, it will simply stop. But here's the part of this story that deserves to be the thing you actually carry with you after this video ends, because it changes the tone of everything that comes before it. Even after that eventual silence, Voyager 2 itself does not stop existing, and it does not stop moving. There is nothing in interstellar space to slow it down, no atmosphere to create drag, no gravitational pull strong enough to meaningfully bend its path. It will simply keep drifting outward in an almost perfectly straight line, carrying with it something bolted to its frame that will genuinely outlast every single person who ever worked on this mission, and very likely outlast the human species itself. Attached to Voyager 2, exactly as it is attached to Voyager 1, is the Golden Record, a phonograph disc plated in gold and curated by a committee led by the astronomer Carl Sagan back in 1977. Etched into its grooves are 90 minutes of music drawn from cultures scattered across the entire history of human civilization, spoken greetings recorded in 55 different human languages, natural sounds of Earth itself, thunder, wind, ocean waves, the calls of whales moving through deep water, and more than 100 images encoded directly into the recording, complete with playback instructions etched onto its cover in case whoever eventually finds it has no concept of what a record even is. Researchers studying both spacecraft's long-term trajectories estimate they will continue orbiting the center of the Milky Way for something in the range of 5 billion years or longer, essentially outlasting the sun and the solar system that built them. So somewhere out there right now, more than 13 billion miles from your kitchen table, that spacecraft is still moving, still humming with the real, measured texture of interstellar plasma, and for at least a little while longer, thanks to a maneuver nicknamed after the birth of the universe itself, it is still listening and still talking back. 3 fragile instruments, kept alive by a piece of decaying plutonium sealed into a metal canister nearly 50 years ago, running on less power than it takes to light the inside of your refrigerator, are still measuring the actual physical texture of the space between stars and sending that information home across a gap so vast that the answer to any single question takes the better part of 2 days just to arrive. The team that built this mission in the 1970s could not possibly have known it would still be delivering discoveries like this one in 2026. They planned for 5 years. They got nearly 50, and counting, thanks to careful engineering, 176-year planetary alignment nobody will see again in this lifetime, and a small group of engineers at JPL who, every year, find one more clever way to squeeze a few more months of life out of a machine everyone, including its own designers, assumed would have gone silent decades ago. The power is still dropping, 4 watts at a time every year, with absolute mathematical certainty. But right now, in the summer of 2026, and that clock just quietly bought itself another year, and somewhere out past the edge of everything the sun touches, a 50-year-old machine keeps drifting deeper into the dark, still humming with the sound of a frequency no human instrument had ever recorded before it, and still sending its signal home for as long as anyone here is still listening. If you want to know the moment engineers confirm the same fix on Voyager 1, subscribe and turn on notifications, because that update is coming within the next few months, and when it lands, you will already understand exactly what you're listening to. But thanks for watching, and I will see you in the next one.